My name is Kevin B. Burke, and I'm the author of Statistical Astrology, the use of irregular seasonality in quantitative time series analysis and forecasting. This video is all about the dimension of time. Few people realize how limited the human perception of time is. I'm going to do my best to illustrate this because it's essential to the fundamental premise of the research, and also because it's limited the statistical options to analyze time series data. I'm also going to explain why we can't understand or measure time without using astrology. There's no time like the present, so let's get started. Actually, there's no time but the present, but we'll work up to that. We have both objective and subjective references for anything that can be defined or measured in 3 dimensions. Let's consider the dimension of length. This is a typical ruler. It's 12 inches long. It's also 30.48 centimeters long. It's 1 foot long, it's 304.8 millimeters long, and it's just over 1.6667 fathoms long. And these are only a few examples of how we can measure and describe the dimension of length. But we understand that inches or centimeters are units of measurement of length. If you take away the measurement, we can still perceive the actual unit of length of the ruler. And if you need any more convincing, consider that you instinctively understand this does not actually measure 12 inches. If you're watching this on your phone, it might only be 2 or 3 inches. And without measuring it, you understand the difference between this image and an actual unit of length that measures 12 inches. We have objective references for everything that can be defined in the 3-dimensional physical world. We understand length, width, height, and weight without needing to measure them. You can easily appreciate the difference between the distance from your house to the deli and the distance between your house and New Delhi. You don't need a scale to know you can easily lift a suitcase that weighs 10 pounds, but not one that weighs 50 pounds. We can't do this with time. Our perceptions of time are entirely subjective. We can perceive the entirety of a ruler. We can't perceive the entirety of an hour. Our experience of time is limited to the present moment. The only correct answer to the question, what time is it, is now. It's always now. We remember other nows that are not the now we experience now when we call these then. And we can anticipate nows that we've yet to experience, and we call these later. But our actual subjective personal experience and perception of time is limited to the present moment. We perceive time as a single dimension. Literally. Time exists for us as a line that extends from the past to the future, and our perception of time is limited to a single point on that line known as now. We can only move in one direction along the line from the past to the future. We know this is not an accurate description of the dimension of time. We constantly speculate about the nature of time. We imagine what it would mean if we could travel in time. Alternate timelines are a staple of science fiction and fantasy, but none of this changes how we perceive and experience time. Memory allows us to maintain the illusion of continuity, but in fact, we live in a perception bubble that maybe lasts 5 minutes. Basically, we're goldfish. Our objective understanding of time depends on how we measure time. The calendar and the clock provide objective references to organize the sequence of thens and laters, and also give us the ability to compare different units of time without actually being able to experience those units of time directly. For example, we know a year is considerably longer than a day, but how long is a day? We're not capable of perceiving an entire day at once. We understand a day is 24 hours, but how long is an hour? We're not even capable of perceiving an entire hour at once. And this brings us to the first important concept. Because we can only understand time when it's measured in terms of the calendar or the clock, we confuse the units of measurement for the thing being measured. An hour is a unit of measurement of time, but we think an hour is a unit of time. Take a minute to let that sink in. It's important. We're so dependent on how we measure time that we rarely wonder how we measure time. We can't measure time unless we can establish some kind of external, observable, objective reference. The external, observable, objective references used to measure time are celestial. All time measurement is based on the cycles of the planets. Essentially, astrology is how we measure time. Now, I'm going to take a few moments here and draw a semantic line in the sand. Astronomy, as it's understood today, didn't exist until the 17th century. The modern science of astronomy is concerned exclusively with the physical and material aspects of the celestial bodies. For most of human history, astrology and astronomy meant exactly the same thing. But in modern times, astrology's gotten a very bad rap. It's true that while astrology and astronomy both seek to understand the universe, they have different objectives. Astronomy focuses on the physical attributes of the planets, while astrology is concerned with the cycles of the planets and how those cycles measure time. The planetary cycles we use to measure time are astronomical events, but because their original purpose was to measure time, they're more accurately described as astrological events. The most fundamental unit of time measurement is the day. A day is defined as the time it takes for the sun to orbit the Earth. And yes, this is a completely accurate definition. For almost all of human history, the Earth was the center of the universe. Copernicus didn't change that model until the 15th century, and by then everything about time measurement had already been standardized. Now, we know that a day is actually the time it takes for the Earth to complete a single revolution on its axis. But we're considering the earliest days of civilization in the 4th millennium BC and the Sumer civilization in southern Mesopotamia. As far as they were concerned, the sun revolved around the Earth. So, back to the day. Sunrise and sunset are the external, objective references that allow us to begin to measure time. A day is defined as the time between one sunrise and the next, or between one sunset and the next. The Sumerians developed a very complex system of mathematics based on the number 60. They were the first people to divide the day into 24 hours, and to further divide it into 12 hours of day and 12 hours of night. And that doesn't at all mean what you think it means. Because we only understand an hour as a uniform unit of measurement of time. But hours are only uniform 2 days out of the year, on the spring and fall equinoxes. The rest of the year, the duration of an hour changes with the amount of daylight. In the 2nd century BC, the Hellenistic astrologer and mathematician Hipparchus of Nicaea was the first person to propose standardizing the hour based on the equinoxes. But this idea didn't catch on until the invention of mechanical clocks in the 14th century. Other than the day, the most important unit of time is the year. A year is an astrological construct. A year is the time it takes for the sun to complete a single cycle of the zodiac. Now, the zodiac is a great circle projected on the band of the ecliptic. From our perspective, the ecliptic is the path of the orbit of the sun around the Earth, but of course it's actually the path of the orbit of the Earth around the sun. Because the zodiac is a circle, and a circle has no beginning or end, the only way to measure the position along a circle is to define an external objective reference point. This point is called 0 degrees Aries, but there are two schools of thought as to how it's measured. Tropical, which uses the spring equinox as a reference, and sidereal, which uses the fixed stars as a reference. The earliest zodiac system was developed by the Sumerians, and the reference point was the spring equinox. The zodiac in astrology has always been tropical. Now, one reason for this choice is that the fixed stars are not, in fact, fixed. Because of the wobble of the Earth's axis, the moment of the spring equinox moves backwards against the backdrop of the fixed stars. And this is one of the most common arguments used by scientists to invalidate astrology, and it's entirely toothless. Hipparchus wrote about the precession of the equinoxes more than 2,000 years ago. The precession of the equinoxes didn't matter because it had no impact on how we measure time. And the primary, if unstated, objective of astrology has always been to measure time. For agrarian civilizations, what mattered was being able to accurately measure the time between the seasons. The zodiac is the basis of the first season to measure time in terms of annual cycles. The great circle of the ecliptic is divided into 12 equal segments of 30 degrees of arc known as the signs. And for the record, the constellations, the groups of fixed stars, have never been used to define the boundaries of the signs. A sign is a unit of measurement equal to 30 degrees of longitudinal arc around the ecliptic. There are 4 objective observable references that divide the year equally. The vernal equinox defines the start of the circle and 0 degrees Aries. The summer solstice defines 0 degrees Cancer. The autumnal equinox defines 0 degrees Libra, and the winter solstice defines 0 degrees Capricorn. Each 360-degree cycle of the sun through the zodiac equals a year. The equinoxes and solstices are the fixed points in the year. The purpose of the calendar is to divide the year up into days and make sure we can accurately predict each upcoming seasonal change. Whatever numbering system's used, the calendar is only accurate if the observed equinoxes and solstices occur on the same dates every year. This is not nearly as easy as it sounds. Because the unit of time represented by 1 degree of motion of the sun along the ecliptic is not precisely the same as the unit of time represented by 1 revolution of the Earth on its axis. When you convert the 360 degrees of a year into days, 1 year equals 365.256 days, and it took over 1,600 years to come up with the solution. The calendar has to operate in integers, so a year has to be rounded down to 365 days. The Julian calendar, introduced by Julius Caesar and officially adopted in 45 BC, was the first calendar to include 12 months, a standard 365-day year, and a leap year every 4 years to account for the 0.256-day remainder. And if a solar year equaled 365.25 days, the Julian calendar would still be in use. The problem is that 0.006 remainder starts to add up. The Julian calendar overcompensates by having a leap year every 4 years, and the dates of the equinoxes and solstices began to slip. Pope Gregory introduced the Gregorian calendar in 1582, and it's still in use today. This calendar introduces a 3-tiered system to determine whether or not a year is a leap year, to account for that 0.006 remainder. The point of all this is our ability to conceptualize units of time longer than a day relies on the Gregorian calendar. And the Gregorian calendar is a matrix that converts abstract astrological measurements of time, 1 degree of arc along the ecliptic, to standardized day-based units of time we can actually comprehend. The most significant limitation of how we perceive time is that we can only understand time when it's expressed in terms of the calendar or the clock. We're like Americans with the metric system. What the heck is 30 kilometers? Give it to me in miles. We can only understand time when it's expressed in terms of the calendar or the clock. But the calendar and the clock are not the only ways to measure time. Statistical time series analysis looks for historical patterns in time, and it uses these patterns to generate forecasts. One way statistics looks at time is through the lens of seasonality. It looks for patterns in the data that repeat consistently. The current approach defines seasonality in terms of the calendar and the clock. The units of measurement of time are also the seasons, and this has created some recursive expectations about seasonality. All units of time measurement are subdivisions of the calendar year. The units of measurement are standardized and consistent, and because the seasons are the units of measurement, the seasons recur consistently following the same sequence. This is an example of regular seasonality. Calendar and clock time, and by extension, the current understanding of seasonality in statistics, are based on the astrological cycles of the sun. And once again, let me remind you, even though we can only understand time when it's expressed in these terms, the calendar and the clock and the cycles of the sun are not the only ways to measure time. In my research, I introduce a seasonal model based on the cycles of the planet Mercury. This is irregular seasonality because these seasons are irregular in duration and also irregular in recurrence. The Mercury cycles don't track with the solar cycles that define a calendar year. These models of seasonality are incredibly complex, and ultimately, the only way to understand them is to map them back onto the calendar because that's the only way we can comprehend time. It's not a perfect metaphor, but part of what I've developed is a microscope for time. When you view a drop of water through the lenses of a microscope, you can see a world of single-celled organisms that are otherwise invisible. When you view time series data through these astrology-based lenses, you can see patterns and cycles that are otherwise invisible. And those hidden patterns and cycles can be leveraged to improve the accuracy of time series forecasts.